Very happy to introduce Robin Scheibler, who's coming from Google DeepMind in Tokyo. Came all the way here to give the talk, so really pleased that he made it. He's going to be talking about generative methods for separation and enhancement. Take it away.
Okay. Thank you very much for the introduction. It is my great pleasure to talk here at SANE. I'm very excited to talk to you about generative methods for speech enhancement and separation. So this is, not all of it is my work, so the idea is more to give an overview of things that have been going on. So I will try to cover a lot of ground, so I hope I make it in time. I will make it in time because I'm the last obstacle between everyone and the drinks. So sorry for that. So first we'll go just background and motivation, what we're trying to achieve in general. Then go more into generative speech enhancement. And this part is more covering sort of different flavors of generative speech enhancement that have been explored in the field. Then we'll go into generative source separation, and this is more covering one specific type of generative source separation using diffusion that I've been sort of working on these past few years. And the last part is more about how we evaluate this method and maybe some pitfalls that exist. And finally, we'll go into conclusion and some maybe quote open problems or things that I think are still very interesting to work on. And first, background. Okay, so speech enhancement, I don't think I need to explain it a lot, but so the idea is that you're trying to say something and maybe there's a lot of noise around, there is some trains, some dogs, people talking music, kind of worst case scenario. And then your speech still has to go through a few things. So there may be like reverberation due to a room or the environment. You may go through like a phone with a low quality codec. There may be some low pass filtering, clipping, your microphone may not be very good. And then you get this speech that's red, so it's not great to listen to. And we would like to put this through neural networks in 2025, and then get the output speech that's really good at the output and use this instead. And the way we have been doing this so far is using like regression-based training methods. So we'll have data sets of noisy speech and the clean speech version of this. We'll feed the noisy speech to the neural network, and then we'll compare this to the clean speech using some kind of distance function, and we will minimize the distance between the clean speech and the estimated speech and try to make the neural network work better. So that's the regression-based approach. So there different areas where we want to use speech enhancement, and this often comes up in the questions, like, is your model real-time, or can you do this and that? So I want to address this first. So usually we think maybe about like low latency, high latency, and low compute, high compute, and so on. And depending on what you do, you'll be somewhere in this graph. And so specifically in this talk, I'll only care about this part, because I think this is how you can get probably the best quality, and we first care about trying to make the best model possible, and then maybe in later work we can try to optimize this. Okay. Another thing that I think is interesting and I'd like to advocate for is speech enhancement conventionally has mostly meant like removing additive noise from the speech. So we have like our input signal, noisy speech is X, is like speech plus noise. And in general, we make the additional assumption that the noise and the speech are uncorrelated. And this means sort of you have like orthogonal signals that are summed up together, so there are good chances you can sort of separate them using a speech enhancement network. So instead of that, I think it's useful now to consider what we call universal speech enhancement, where we don't just have like additive noise or a single type of distortion, but we have many distortions at the same time. So you may have additive noise and reverb and clipping and low pass and so on, as I described in the first slide. And when you do that, something happens is that the target signal that you want to recover may not even be in the in the input signal that you have, so or at least not all of it. So for example, if you take the example of clipping, then in some areas your signal is clipping. Okay, you know maybe it's larger than this, but you don't know the exact value. If you take the example of low-pass filtering, you may be missing like the whole band of the signal. For a codec, for example, a codec may remove signals that the codec thinks is not useful only in some areas of the spectrum. And you may have very, very weird things, or you may have like additive noise is very strong only in some part of the input, and your signal is not available there. And in this case, when you're trying to train your neural network, as I showed on the first slide, where you're just like measuring the distance between the target, this may not provide really useful information because there may be like many different reconstruction possibles that are all meaningful, but that don't really match what you had in the target. So this is ambiguous, and in this case, like the regression-based training will not work that well. So this is the motivation to go more towards generative methods. And here, I just give sort of, there are some equations that look mathy and like very complicated, but it's just sort of to give an idea of what we're trying to achieve. I'm not saying that is exactly what we'll be trying to do. So we have a model of the signal X that goes through some maybe complicated function that maybe we don't really know exactly, and this is what we get. And then what we want, the way we want to get the enhanced signal is by sampling from a distribution P of speech that's conditioned on the input signal X. And then we may, so this will be the generative model. And then we may want, in some case, to add some constraint that the signal that we get, S hat, is consistent given this distortion function with the input signal that we had, up to some epsilon that we may not know. So this is more like conceptual. And there may be different ways to implement these different parts of the system. Okay? Then another thing that I think is useful to consider is that there are different ways of modeling the speech probability at different levels. And one level that is very straightforward to at least understand, but maybe difficult to implement, is doing it directly in the waveform domain. So you're trying to model really the time domain signal, or let's say any sort of one-to-one mapping with the time domain signal. So there's a lot of information. It's a very long time. There are lots of very small details that may not be so useful. Then instead, people have been trying to do instead like latent space modeling. So this may be different types of space. So you could say, Mel spectrogram might be one of them. So you reduce the information that's in the signal to sort of focus on what's important. Or you could use some self-supervised model to get these features. One problem is that these representations may be lossy, so you may remove some information. You may want to tune, what is the information you remove, what is the information you keep, and so on. So we would like, for example, to keep like speaker ID and semantics, but usually we have no guarantees that this is what happens. So in the talk, I'm roughly classifying these models into like waveform models and then latent models, and then there may be some hybrid models that sort of consider both of these features. Okay. Also, I color code it. So like in green, I will have more like the waveform types of models, and blue, the latent models. And many of these generative methods, so for speech enhancement, they get their roots in speech synthesis. So it's useful just to quickly recap how this works. So for speech synthesis, we'll have some text. And then from the text, this may not be true for all systems now, but at least it used to be this way. We will first predict some features from the text that represent the speech corresponding to the text. And then from these features, we will use a vocoder to sort of create the time domain signal. And this will be sort of a template to make a speech enhancement system. Okay? There are also different flavors of generative models. So there's autoregressive models that do like next token prediction. And these have been used more for sort of the feature prediction part of these systems. And then there are like GAN-based models. And these have been used more for like the vocoder part, so taking the features and making the waveform out of it. Okay, and here is just the hi-fi GAN, where there is both like a discriminator where you try to predict whether the input is real and fake, and also some feature matching loss, where you have like trying to minimize distance between the features in the discriminator between real and fake data. Okay. And finally, I just want to give like a short introduction to diffusion models, even though there was a talk before. because we will use this more in the speech separation part later. So for diffusion models, we have a forward process where we start from the clean data that we're trying to model, and then we have a fixed process that take it towards noisy data. And then we will try to reverse this process. And using this reverse, here's an SDA. There are different ways to write this. And then this is where the DNN will come in. These models appear actually both in more like the latent type of models, where they are used to generate features, but then they require a vocoder to come back. So for example, like audio LDM, latent diffusion model. And then there are also some other methods that use diffusion to predict the waveform, like for example, WaveDiff, which is a diffusion-based vocoder. Okay. And now I think we have all the things that we need to go into the models for generative speech enhancement. And these features works from different places. The first one, I think, is one of the first methods that was out there for generative speech enhancement. It was presented actually at WASPA in 2019. And here is just really applying the template from the speech synthesis model to speech enhancement. So here we don't have text, and instead the input to the model will be the noisy speech. And this was really prompted by 2019, the vocoders became really good. I think before that, we mostly had like speaker-specific vocoders, and then they started to be able to do multiple speakers. And then the idea was, okay, if you get noisy speech, maybe you can just predict the features and just make up completely new speech, but that sounds really good, but that's sort of still have the content. And in this particular paper, the features used were MEL spectrogram, so there would be a model that predicts the clean MEL spectrogram from the noisy input, and then the vocoder would recreate the speech. So they tested different vocoders like WaveGlow, WaveNet, and World. So and that worked pretty well. And this prompted like further research in the area. And then there was a MIFER, which is a model that was developed at Google by my colleagues. And so here the idea is very similar. So it uses like the same structure, but instead it's just like everything is beefed up. So it will use like a really strong encoder for the features that has been pre-trained on lots of text. So it uses these USM features that were trained on 12 million hours of speech using self-supervised learning. And then the idea of the model is that it takes this feature of the noisy speech and make them clean speech. So thanks to the self-supervised training, you expect actually that these USM features they will already reject a lot of the noise. So that already helps to clean up things. And then they use also like a stronger vocoder to reconstruct the speech from these features. Okay, and the training of this model follows really like the template. So first you have to train the clean feature prediction model, and then you have to train the vocoder, and then at the end you can do some joint fine tuning to sort of improve still a little bit the performance. Okay. However, these models have they have some advantages. So they give really clean speech, and you can sort of apply the speech-specific knowledge. So if you have a really good like self-supervised learning methods, you can use this to learn all the features, and then you can also improve you can train your vocoder only on really clean speech, so that you can only generate clean speech. There's no way you can generate noise. On the other hand, they have some disadvantage. So when you do the feature extraction, you lose lots of information that's in the speech. So in many cases, you lose the timing of the speech or like the phase information. You may lose some speaker identity because these features are trained mostly for ASR, so they don't really care about speaker identity. So actually, when you use the system, it may sound very clean, but it may sound like someone else. Or even in some cases, it may say something else. If the speech is very noisy, then it will still try to make up some speech, So you have some hallucinations. So for some use case, this is fine. If you just want to have more clean training data, you don't really care that the content is the same, but just that the data is clean. So instead, you may want to, okay, let me go back. So that was one of these models that I was calling like more latent space model, where you do the cleaning in the latent space feature. So instead, you may want to have a generative model that directly works in the waveform domain. So this one is SGMAC, so that stands for, I think, score-based generative model for speech enhancement. It doesn't work in the time domain, but in the compressed spectrogram domain, but still retains the phase, so that it's like a one-to-one mapping to time. So using this model, you can still predict like phase-exact signals, which makes it a lot easier to evaluate, for example. So you can use a good old SISNR to measure the fidelity to the target, which is nice. It's been really, really popular. And there have been many extensions of this work to dereverberation, to bandwidth extension. I think there have been some extensions where you combine it with a regression-based model. Oh, I haven't explained how it works. So here it's a diffusion model, but it's a little bit a twist on the original concept. So instead of starting purely from pure noise, you will start from a noisy version of the noisy speech, and then you will do the reverse process will bring you to the clean speech signal. So this is the idea here. Go towards something that's very noisy, and then your reverse process, which is actually the denoising process or the speech enhancement part, gets you back to the clean speech. Very good. Okay. Yes. Let's go to the next one. The next one is another time domain model. I think it was maybe the first diffusion-based speech enhancement paper that came out, and it was directly targeting like this universal speech enhancement and restoration. And although it's a time domain signal, if you look at it, a time domain model, if you look at it carefully, it has actually part of it that does feature prediction or some type of latent feature prediction, and then one part that is really a pure vocoder. These are, so in blue you have the clean feature prediction part, and then in green is more the score model of the diffusion. So this one starts from pure noise and generate directly the clean speech. And the nice property of this one is that all of it is trained jointly. And because it has this sort of split architecture, you can add a few auxiliary loss functions that help you shape the features that you use for the generation. So for example, here there is a loss that works more on the waveform so that you maintain phase information, and then the one of the feature that sort of make the features look like Mel spectrogram. And that worked quite well. And then I did an extension of this work where we tried to further improve the features. And to do this, we replaced these more sort of regression-like losses on the features by a GAN style loss, hi-fi GAN style loss, where you do like you have this discriminator and also some feature matching loss. We also replaced used the latest diffusion sort of model, or add the EDM style normalization diffusion model would help a lot. And we added some fine-tuning procedure to sort of make sure the model keeps the content of the speech. Okay, and here we have some comparison. We have in red like a regression-based model that was, I think, band split RNN. Storm is a version of SGMAC, so the diffusion-based speech enhancement of the previous slide. But it's a hybrid version, so it has a regression part and a diffusion part, and in green is the almost purely diffusion-based model, so universe and universe plus, the one that's slightly improved. The metrics are word error rate, so that measure more signal retention, like the semantic retention, and DNS-MOS measures the quality of the speech. This was evaluated on the speech signal improvement challenge. And this is real data, so there is no ground truth. So these are really measured noisy speech. And we see that essentially using generative models for speech enhancements will give you really, really good DNS moss. So you get, this is really in distribution, but often it doesn't really, it's a non-intrusive metric, so your signal may be gibberish, and you will not know it. So having a good word error rate then tells you that you're actually doing a good job. So you want to have both. And the Universe++ did a good job in this case. Okay, so this is the end of the part on the speech enhancement. And what I'd like to sort of for you to take home is maybe try to move from this simple or single degradation sort of enhancement towards this universal speech enhancement, because this is really what's useful. I showed like 3 types of framework. This one that is more working in latent space based on parametric resynthesis, which works really, really well. It's really, really powerful, but it's also fairly difficult to evaluate. It's hard to know if you did a good job at the enhancement. Then there's this SGMSE, diffusion-based framework, that's also really popular. There are many work on them, many improvements of the diffusion process to have better enhancement. And then finally, this sort of hybrid approach that works where you have some features and you have some laws that help you shape these features to keep what you want, that work together with a diffusion model to create the clean speech based on these features. Now we'll do a little bit of a gear shift and go into the source separation. And this is a little bit opinionated source separation, so I'll present just really one way to do a generative source separation based on the work I did together with my colleague at Naver in my previous job, and the work I did with my colleagues at DeepMind, John Hershey, Arnaud Doucet, and Henry Lee, that we presented actually at the WASPA a few weeks ago. So for speech separation, it's a little bit different from speech enhancement. Also, it's a very related problem. In this case, you have a mixture that is not speech and noise, but maybe you have speech and speech. In some types of separation, you have music, so maybe you want to separate vocal, guitar, bass, or universal. You may want to separate all sounds that have been produced by a different source. Or maybe you have a combination, we have speech, speech, and noise, or speech, speech, and trumpet, or something. But in this particular case, I will focus just on speech, speech in the experiments. And maybe it's not directly clear that speech separation can be a generative task, so I would like to motivate this. So in this graph, I show 2 sources. So it's a 3D graph, so I think this axis here is time, and then the 2 other axes are the waveform amplitude for like speaker 1 and speaker 2. Now you can do a change of basis of these 2 axes. You do not a rotation, but you multiply by a Haar matrix, I think, and then you get the sum and difference of the sources. And the sum of the sources is in purple, and the difference is in black here. So really, when you do a source separation, all you're given is the sum of the sources, and what you're missing is the difference. So you could say that the source separation is a generative task where you need to generate the difference of the sources when you are given their sum. And then if you're given the sum and difference, then you can just invert this change of basis and go back to source 1 and source 2 separately. Now we want to put this more into a mathematical framework where we can express this. And to do that, we can introduce projection operations that are here on the right. So it's a P and the P orthogonal, so the orthogonal projection. So I have a graph that is similar to the one in the previous slide, except I removed time, and now we have 3 sources, okay? And the axis of the sources are the 3 small arrows here. So we have X, Y, Z, or source 1, 2, 3. And I have rotated the space so that the vector that contains all 1s is pointing up. now the vector of all separated sources is this S, and it has like source 1, 2, and maybe 3 in the rows. And when you multiply this vector S by this projection matrix P, what you obtain is this point that is here on the axis that is spanned by the all one vector. And this axis is nothing but this vector of all one multiplied by the average of the sources. And the average is very much related to the sum, or you could say it's the same thing, just scaled by k. So in the problem of source separation, what we know is this point. And what we would like to do is we would like to find this missing component here. And once we have it, we can go back to this point S and recover all the sources separately. Okay? So in our work, DivSep, we presented two years ago. So we use this to create specific diffusion process here. So we create a forward process that will take us to the sources that are separated at x0. And then at each time step, you look at the difference of these sources. So you project with this 1 minus p projection matrix. So, okay. So the 1 minus p projection matrix projects on this plane here. This is the plane of the components that we're missing. So in this process, at each time step, we look at the difference between the sources and we subtract it a little bit. So we remove a little bit of the difference between the sources at every time step. So as you go further in the process, you will converge to the mean of the sources. And then we also add a little bit of noise at each step. So now we have a forward process. So we can apply all the machinery of the diffusion framework. And by this framework, we can find the reverse process that will take us from the noisy mixture of the sources back to the separated sources. And for this, we'll need, we will train a neural network, like the SCORE network that does it. So when we want to sample, really, we will sample like xt1 and xt2 at time t that are centered around the mixture of the sources, and we add a little bit of noise. And then we use our SCORE network and this reverse stochastic differential equation. We will solve it, and we can go back to the separated sources. And that worked. So that was a nice proof of concept. Here I compare it to, I think, conf.tasnet. So we have, I think, 14 dB SDR, so it means we separate the sources, but we cannot really do, we didn't do better than the regression-based model, so it was not really perfect. But we got good DNS moss, so it was a good generative model doing like things that are sort of, they can fool the non-intrusive metrics. So the problems that we had was that first, because of the SD that we used, there was a mismatch between the xt according to the forward process, where you still have a small term that depends on the unknown sources S. It is scaled by some exponential term in t, so it should become very small, but still it is there. And then what we can sample from when we start the process is this S bar plus some noise. Then another problem is that the process was not mixture consistent, so we would generate something that maybe did not correspond really to the mixture of the sources. When we add the noise on S at time t, so at the end of the process, we would also apply the noise in the whole space, so this would sort of smear the mixture, which was the known signal. Another problem of the diffusion-based approach is that we're sort of constrained by this forward process. So if we want to change the algorithm, we have to find like a new process to do that. And this also constrained like the noise and the separation schedule that we can use. So we tried a new approach based on flow matching that we presented at WASPA a couple of weeks ago. So we did a few improvements. So one is to replace diffusion by flow matching, which is at least, I can't say it is better, but at least it is a little bit more flexible. We added also strict mixture consistency, so that throughout the flow matching process, we always maintain mixture consistency. And finally, we also treated the permutation equivariance because the order of sources do not matter. So I'll just give a short primer on flow matching. So flow matching like diffusion allows you to transform one distribution into another. So for example, like a Gaussian distribution into some other distribution that depends on your data. And you also do it with a differential equation, but here the differential equation is a lot simpler, and it only depends on this velocity that is defined by a neural network. So you really need to sample from your distribution at P0 and then solve this equation and to sample from the target distribution. And the difference with the diffusion that makes it a lot more flexible is that you always choose to take like straight paths. So during the diffusion process at xt, you always take xt to be a linear interpolation between P0 and P1. And you train your velocity network by minimizing these objective functions. So you can look at it this way. So this is the network you want to train that is here, and this is your regression target. So the regression target is just the difference between the starting point and the end point. And we apply this to the separation problem just before. So first, we want to have a mixture consistent flow. So to make sure that the mixture flow is that the flow is consistent, first we sample from x0 to be the mixture vector. So this vector just contains the mixture repeated in every component. And then we add a noise, but we add noise that lives in this subspace that has zero mean. So that the mean of this vector x0 is the mixture itself. Now we define the ODE, like the differential equation, also to be multiplied by this projection vector, so that when you solve it, every time you add a small increment, you never go out of this subspace. So all the increments lived in the pink subspace, so that in every part of the path, you always have the same mean. So you're always mixture consistent by construction. Then we also treat the permutation equivariance so that you could go in two directions. So for example, if you consider two sources, the difference of sources is ambiguous up to a sign, because you could have like, source 1, source 2, or source 2, source 1. So their difference could just be changed by a sign. So you want your process to work whether you choose to go right or left in that case. And finally, we did some improvement on the loss function that are more sort of heuristics. So they're not, we deviate a little bit from the flow matching theory. Okay, so we compare this on two-speaker experiments with a LibriVox dataset, and we compare to some regression-based method, for example, using ConvTasNet, or this is a low conformer networks. This is similar to TF GridNet in construction. Here we have two methods, diffsep and edsep, are the previous method or an improvement to the previous methods that use the diffusion process. And here in blue are this flow matching based separation with a different number of steps. And we see that the flow matching based method sort of gives higher metrics, like the metrics are SNR and Polka and DNS-MOS. So we were quite happy with that. I will skip these samples, and I have a more sort of in the wild separation. So here, this is the original recording. I think it's a YouTube video. And then we take the output and we apply the separation, but we also apply a post-processing step using Mefer to improve the quality. So here's the original recording.
Ridiculous. No, you know what? Give me a break.
You can't keep doing this to me.
Late.
And you're a mess when you show up to work.
Unfair.
And you serve your customers terribly. I'm doing all your work for you. Every time you serve somebody, I got to comp them the way you treat them. No. You know what? Take your apron off. Ridiculous. Man, you can't keep doing this to me. And you're a mess when you show up to work. And you serve your customers terribly. I'm doing all your work here. Every time you serve somebody, I got to comp them the way you treat them. No. You know what? Take your apron off.
Yeah. So it's actually quite difficult to find videos where speakers really overlap. So, Okay, so here's the the take-home message for this part. So diffusion and flow matching, they can be modified to include like mixture information. I think we have a clean formulation using projection matrix to express these problems. Also, I think flow matching is a really flexible and stable alternative to the diffusion methods. So this type of generative source separation, there's potential to address some shortcomings of regression models, like, for example, regression to the mean, where when both sources are active at the same time, they become a little bit smaller in the output. It's not the only approach. So there are some other alternative approaches to separation using diffusion models. So, for example, SEPDiff was presented in the same session as diffsep at ICASP, which was interesting. And it uses more sort of a latent space similar to the MIFER or parametric resynthesis, where it does the separation using a diffusion model, but in the MEL spectrum space, and then uses a vocoder to bring back the sources. So that also works. And then there are some other approaches, like you could use a diffusion model in the latent space, but then use some conditioning to separate the sources, like in language queried separation. So for example, for speech and speech, it's more difficult to have meaningful labels for that. But this is also, I think, a promising approach. Okay? And now I want to go more into the evaluation part. So how do we evaluate these models, or what are some problems? And this part is motivated by my participation in the organization of the Urgent Challenge with many people that are, I think, most of them are listed here. This is a collaboration with the people at TU Braunschweig and CMU and Shanghai Jiaotong University and Meta and myself at Google DeepMind and Anurag. So there are several questions. So when we go from simple enhancement to universal speech enhancement, how do we evaluate this model? So how do we make sure that this model generalize to various distortion types? It's difficult to cover the full range of possible distortions of speech. And how do these models deal with the out-of-domain data, for example? And also how to do the evaluation. So what metrics should you use? So especially, for example, strongly generative enhancement models are quite hard to evaluate. They are prone to hallucinate very convincing speech. For example, when there is a strong noise or when the signal is partly missing. There are some problems with measuring, for example, speaker identity. The prosody may change. And one big problem is that signal-based metrics do not work for these models. So it's quite difficult to I mean, they could give you really bad metrics, like conventional metrics, but still have actually really good output. So we don't really know what's going on. And so to sort of investigate these questions, we organized the Urgent Challenge. Urgent stands for, what was it, universal, robust, and generalizable enhancement. And the NT comes from enhancement at the end. And this was a good name because every time you get an email about it, you're like, oh, that looks really urgent, and you look at it first. We're organized, I think we're now at the 3rd edition of the challenge that will be organized at ICASP next year. But what I will show you is about the challenge that was organized at Interspeech this year. So we prepared a large data set that contains lots of noisy samples and a number of distortions. So this year we concentrated on multilingual. So we had several languages in the data set. We had up to 7 types of distortions. And we also included a large number of metrics to measure these signals and subjective listening as well. Okay, so that's the evaluation strategy. So that's from the paper that was led by Kohei Saijo, where we sort of do the reflection on the learnings of the challenge. So we use the really 4 types of metrics. So we have some non-intrusive metrics. So we use DNS-MOS, NISCA, UTMOS, and this usually tell you, how natural the speech is. We use also a battery of intrusive metrics. So we have Polka-PESC, Story for intelligibility. There is SDR, MCD, and log spectral distance. We have some task-specific or task-independent and dependent metrics. So SBS was a sort of distance metric in latent space. LPS measure phoneme similarity using a phoneme recognition model. So this is sort of similar to word error rate, but will be less sensitive to language of the language of the samples. Speaker similarity and the character error rate from an ASR model. And finally, we had the subjective evaluation using P808 protocol, where you have people listen and sort of rate how good it sounds. The final ranking of the teams was based on the average of the ranks in each of the categories, I think. Okay. And if you look closely at the table, there's actually a peculiar model that is not the first model. So I think this is ranked by the rank on the right. And if you look closely at this model does really, really well in the non-intrusive metrics. And it does really, really poorly in the intrusive metrics. And interestingly, it does really, really good in the subjective evaluation as well. So we had people listen to it, and actually it sounded good. So this is team 13, and this uses very, like a strong MIFER type, so latent type of restoration model. Yeah, so I prepared some samples, and the samples were provided by Wataru Nakata, who's actually the author for this entry in the competition. We did follow-up work on the evaluation, especially the multilingual evaluation. This was led by Marvin Sack at TU Braunschweig. We performed the P808 subjective listening tests in, I don't remember the exact number of languages. Maybe Shinji remembers, maybe that was 7 or something. So I just picked 2 to make it simpler. So there's English. English was included in the training data. And then we also did some tests on Japanese. And Japanese was not included in the training data, so that was blind. The participants did not know we would evaluate on this. And here we see the team 13 topped the score for MOS. And it even did really well in the unknown language. And here, this is the first entry, and the first entry is a purely discriminative method that was the top ranking team in the challenge. And this one also does relatively well on MOS score, but it doesn't do as well as team 13. But instead now, if you look at the content of the speech, so this is the phoneme similarity. So this measures like how similar are the phonemes in the target speech and the enhanced speech. Then the purely generative model actually is pretty degraded and suffers a lot, especially when going into the unseen language. So let's listen to the English maybe. Well, this is the noisy speech. So these are very noisy samples.
That was a traffic accident, so you need to call an ambulance and have the police take care of the rest.
Okay, and here's the output.
That was a clampet accident. They be mean to call an ambulance and have the police take care of the rest.
Okay, that's and, here's the Japanese sample. I think it's hard to tell when listening on speakers like this.
Right. Even the touring linguistics, no one was used.
So, okay, so maybe for Japanese speakers, maybe notice that it's really weird, but it is. It is really weird. It actually sounds even a little bit like English. Yeah, okay. Maybe something like French. Okay, so I think we need more investigation into evaluations. So the urgent challenge is still ongoing, but I think we're reaching the end of the competition. So we have to submit results soon, I think, and we're also organizing a special session together with Marvin and Zhaoheng at ICASP 2026 on the promise and perils of generative AI for the evaluations of speech and audio. And I think there are some papers more about like evaluating the output of this generative speech enhancement model. And what we also wanted to explore is how we could use generative AI and maybe speech LLMs to evaluate the quality of speech in general. So there are like two angles on this. All right, so I think we're at the end of my presentation. And I just wanted to conclude by sort of still some open problems or I think what I think are interesting areas to investigate. So one is this gap that we have between latent and waveform level models, where like waveform level models are really easy to evaluate, but then they're more difficult to. They tend to retain more of the input noise, and they tend to have less sort of long-term consistency in the quality, I think. Whereas the latent models are really, really good at denoising, but then they're a lot harder to evaluate. And I think it would be nice to have sort of like hybrid models or like a compromise between the two, where you have really, really maybe latent enhancement, but still sort of you keep consistency with the high SNR part of your input, or you're still able to sort of compare with your input mixture where it makes sense. Okay. The second is related to the last part, to sort of come up with a holistic evaluation of speech quality, and maybe going beyond just comparing really many metrics. So, for example, can we have a model that describes the audio quality? So, can it say, whether this is grainy or if it's lots of, I don't know, like describe the artifacts in the audio? And there are actually some preliminary work going in this direction. So I think this is very nice, and I'm really excited about it. Then, of course, universal speech enhancement. Something I haven't mentioned that I wanted to mention, I forgot, but in my, I think enhancement and separation now are considered different problems, but they're not really different problems, because we have lots of recordings with many speakers, and we want to maybe enhance both of the speakers and also separate them. And of course, this raises questions about like target ambiguity. If you have several talkers, how do you sort of select the targets that you want and the ones that you don't want? Finally, like training and the generalization of this universal speech enhancement model is very difficult. So I think now at the moment, we just design very complicated augmentations pipeline to try to cover as much as possible of the distortions that we get in real data. And whether this is, we managed to cover them all or not is difficult to tell, or it's difficult to automate. So distribution matching is the same. And finally, I think that we're unsupervised and semi-supervised training methods. They seem to work well for separation, but there hasn't been so much progress made on unsupervised training for speech enhancement models. There are some methods, but they have not really reached the quality of the supervised methods. And finally, okay, those are all the usual suspects. So you have these big models, you want to make it faster, lower latency, and so on and so on. To make real-time or long-form models using diffusion, there are actually some works on autoregressive diffusion or rolling diffusion voicing, and so on, that have not been applied yet to audio. So I think these are good starting point. Yeah. So, okay. Key takeaways. Generative models are great, and they're a key ingredient for universal speech enhancement. There are very different flavors of models that we can play with, explore. I showed the framework for resource separation based on flow matching, and evaluation is really, really important. Okay. Finally, hiring plugs. We just got budget for some interns. We have 2 interns opening, one in Cambridge, one in Tokyo. So if you're interested, come talk to me or John. And we haven't started the hiring yet, so, but we can contact you when this starts. Okay. Thank you so much for your attention.
Thank you for the great talk. Maybe I misunderstood some part of the your separation by flow matching is really sophisticatedly designed for additive mixing process. But maybe the real audio mixture may contain reverberation or something like a universal speech enhancement. Maybe audio is clipped or already contain codec artifact or something. Can we apply something similar of your technique to the such kind of degraded mixtures?
Okay. Thank you for your question. So I appreciate it. I think there's an easy solution actually. You're completely right that if you have this hard mixture consistent process, you will not be able to tackle distortions that are not linear. However, the fix is easy, is that you can just drop the part that enforce mixture consistency. And then the flow matching on that slide is really just interpolating between these 2 distributions. So you can apply the same algorithm minus the projection step.
I see, thank you.
Is it fair to say that the flow matching based speech separation is a better variant or an evolution compared to, say, deep clustering and spectral masking based developed by Merle? Or you're not very familiar with that one?
No.
It's newer, right?
Yeah, it's newer, yes. So
it's not based on spectral masking either.
It's not based on spectral masking. No, that's right. So this is really a time domain model. So it generates the waveform directly.
Thank you. And what about computational complexity?
What do you want to know exactly? It's a fairly big model, and there are many steps. So
Right.
I don't have an exact complexity to tell you, but it's the model we used. I should check the paper, but it's tens of millions of parameters, and we use I think 25 steps, but we had like it worked quite well with 1 steps and 5 steps. So I think potentially you could make it fairly efficient.
Thank you.
Mm-hmm.
Thank you for your talk. I had a question. In the results that you showed, how come the team 13 performed well on the subjective listening task? Because the audio that we heard had like a lot of artifacts. So if it's subjective listening, shouldn't it like filter that out?
Okay, maybe I was not completely fair in the selection of the sample. Is probably. And the other thing is in this table, I think for the outcome of the competition, we only did the subjective evaluation for English because of time, and the model was trained on English. So I think the output is not that degraded in general. So I think on average that was still good. And when we looked in the follow-up work on the multilingual evaluation, I think it dropped from first place for the other languages, but it was still doing pretty good actually.
Okay, thank you. Thanks.
Tk you.
We should take it offline.
Okay.
We're going to be late for the party.
That can.
So let's thank Robin again.